For any two non-empty sets A and B, if the Cartesian product of A and B equals the Cartesian product of A and C, then the set B and C are equal. Okay, let us begin. So what we'll do, we'll first consider an arbitrary element. So let that arbitrary element be denoted by B. So let B be the arbitrary element. So here what we'll do, we'll suppose that B belongs to the set B. Now the reason why we're choosing only B here, because our goal, the strategy that we'll be applying here is that since we need to show here that the set B equals to the set C, so here we will be showing that B is a subset of the set C as well as the set C being a subset of the set B. So first we will start by proving that B is a subset of the set C. So here that's why we're considering an element B which is a member of the set B. That is the strategy that we're using here. Now, if B is a member of the set B, we can also say that A comma B is going to belong to the Cartesian product of A and B for all values of A, belonging to the set A. So any values of A that we pick up, this is always going to be true provided B belongs to the set B. And that means now we can rewrite this statement as the ordered pair A comma B that's going to belong to A, the Cartesian product with C. And here we are using the given fact that the Cartesian product of A and B that's equals to the Cartesian product of A and C. Fine. So we have the ordered pair A comma B belonging to the Cartesian product of A and C. Now using the definition, we now have the first element which is A that's going to belong to A, and we have B belonging to C. But we have already established that A belongs to the set A. Since A belongs to the set A, so this simply means that we have the element B belonging to the set C. We started out by considering B belonging to the set B, and we were able to show that that same element B is also a member of the set C. This simply tells us that B must be a subset of the set C. Fine. Next, what we'll do, we'll try to show that C is also a subset of the set B. So this time we're going to consider another element C, which is an arbitrary element, and it belongs to the set C. In essence, we are saying that the element C is a member of the set C. If C is a member of the set C, can we not say that A comma C, this is going to be a member of the set, which is the Cartesian product of A and C for all values of A belonging to the set A. Fine. Now that means we have the ordered pair A comma C belonging to the set, the Cartesian product of A and B, since it's already provided to us that the Cartesian product of A and B that's equals to the Cartesian product of A and C. Now this means that A belongs to the set A and C belongs to the set B. A belongs to A, we have already established that it's a true statement. So that means C is going to belong to B. We started out by considering the element C belonging to the set C, and we have showed here that C also belongs to the set B. So this implies that C must be a subset of B. So previously we showed that B is a subset of C, and now we have shown that C is a subset of B. That means since B is a subset of the set C and C is also a subset of the set B, this means that B must be equals to the set C, where provided that the Cartesian product of A and B equals the Cartesian product of A and C. Hence proved.